Everybody, well done, Alex Wein. I'm excited to have him tell us about the work he's excited about.
All right, yeah, thanks. So, I'm Alex. I'm excited to be a postdoc here for the semester. So, here's the kinds of problems I'm interested in. Let me just give you an example. So, finding a clique in a random graph, a clique being a fully connected subgraph like the one shown in red. There's actually a few different variants of this question. So detection means I give you a graph. Either it's just a random graph, or it has a planted clique in it, and you have to tell me which one it was. We could also talk about recovery. That means I give you a graph with a planted clique, and you actually need to find the vertices of the clique. Or we can talk about optimization. This means I give you a random graph with no planted clique, and you just have to find the largest clique, as large a clique as you can. These kinds of problems often have what we call statistical to computational gaps. So for the clique example, plant a clique of size k in a graph of n vertices. And we think about either the detection or recovery question. It turns out it doesn't matter. Here's kind of the phase diagram we have. If I'm willing to kind of brute force check all the possible cliques, I can succeed as long as the clique size is bigger than 2 log base 2 of n. That's just the size of the largest naturally occurring clique in the graph. But if I want a polynomial time algorithm, we actually only know these when the clique size is order of square n. And so in the middle, we have kind of this hard region where we believe it's fundamentally hard. There should be no polynomial time algorithm. And we'd like to kind of understand why that is, and hopefully understand why that is in a unified way that applies to all kinds of different problems. So the low degree polynomial method is one particular framework for trying to understand these things, and I will tell you a bit about it. So historically, this originated from the sum of squares literature. And the idea is kind of quite simple. You just want to study a restricted class of algorithms, namely low degree polynomials. So by this, I mean a multivariate polynomial that takes the entire input. Maybe taking a whole graph with one variable for each edge, either a 0 or 1, telling you if that edge is there. And the output, it depends a bit on the setting, but maybe, for instance, the output is supposed to be like an indicator vector that is supposed to be the position of a large clique. And when I say low degree, you should have in mind maybe logarithmic degree. Depends maybe a little bit on the setting. So it turns out, luckily, like lots of leading algorithmic paradigms can actually be captured by this kind of framework. For example, spectral methods or power iteration, and also approximate message passing, and a few other things. And what has been realized in recent years is that maybe amazingly for a lot of these statistical problems, so these are problems that roughly have some kind of a planted signal buried in some kind of noise. Low degree algorithms are actually as powerful as the best algorithms that we know. And so I want to talk about the flip side, the lower bounds. So how can we prove that all low degree polynomials fail to solve the task? The reason we want to do this is because this would constitute some kind of evidence that the problem is actually hard. And in particular, can be used to formally rule out specific things like spectral methods or AMP and so on. So I want to talk about 3 different types of problems. Like before, prior work focused on detection, and then I want to talk about some new work where we kind of extend this framework recovery and optimization problems. So let me jump right in. Detection, remember, we want to hypothesis test between 2 possible distributions, right? I give you a graph, either it comes from a null model, which is just, say, a random graph, or it comes from a planted model, which would have a planted clique in it. And we want to ask ourselves, is there a low degree polynomial that can solve this problem? Right? This means a polynomial that takes in the whole adjacency matrix, outputs just one number. And what does it mean to succeed? We want that number to hopefully be big if there is a planted clique and small if there's not. Formally, this turns out to be the quantity we try to compute. So it's maximum over polynomials because we want the best one of like the mean value in planted divided by the size of the fluctuations in Q. right? So if this thing is big, say tending to infinity, this means in some sense that degree D polynomials succeed at distinguishing these two distributions, whereas if it is, say, bounded, this would mean that low degree polynomial is big.
You're restricting the expectation under Q to be 0 or something?
No, I'm not here, but there is like an equivalent formulation of this that is, yeah, there's a similar form of this where you do restrict it to be 0, it turns out to not really matter. Yeah. So, okay, two sort of fortuitous things happen here. One is that you can actually compute this thing using basically just linear algebra on the space of polynomials. And the second is that this thing actually seems to make all of the correct predictions for these statistical problems, pointing clique, sparse PCA, et cetera, et cetera. Right? This thing really is big in the easy regime. So that's detection. Let me talk quickly about recovery. So here's another problem to motivate why recovery is important. Very simple problem. It's an n by n matrix. There's a k by k planted submatrix somewhere. And everything is Gaussian with variance 1, except the planted submatrix has an elevated mean of n. Okay, and the goal is just to find this submatrix. Why I like this problem is that it has a detection recovery gap. And what this means is that while detection is quite easy, you can just add up all the entries of the matrix. Right? And because you have this elevated mean, this will help you pick it out under some conditions. But if you actually want to recover, actually find the submatrix, this seems to be harder. The best way we know is basically to use the top eigenvector, and this requires some stronger condition. Right? So recovery seems strictly harder than detection. And so generally speaking, if you can show detection is hard, this means recovery is hard. So that's one way you could hope to show recovery is hard. But in this case, the real challenge is how do we show recovery is hard in a regime where we know detection is easy? Right? We have to do something other than leverage the detection hardness. Yeah.
For such a regime, is there like some average hypothesis in problem that shows how the recovery is
That's a great question.
like a no which one?
Yes, so we don't know one. So you can do things like correct the mean, correct the variance. Those don't work. They do shrink the gap a little bit, but not all the way. So yeah, I don't know any hypothesis testing that can sort of. There's not like a different null model you can invent that will close the gap. It seems to kind of be more fundamental. Unless the null model is something quite complicated, then maybe we wouldn't be able to analyze anyway. Yeah, but that's a great question. And so, okay, time, but roughly for these recovery problems, we do have a way to analyze low degree polynomial in this setting. So imagine you observe something that's kind of signal plus noise, and the small x is something we want to estimate. Say maybe it's just the indicator that the first coordinate is in the submatrix. Right, this is the quantity we'd like to understand. It's like how much correlation can a low degree polynomial get with the thing we want to estimate, suitably normalized. We have a way, that's a very natural thing to write down. It turns out to actually bound this, we need sort of a trick where you apply Jensen's inequality only to the signal and not the noise, and this somehow simplifies things enough. Okay, and this now yields kind of tight results for planted submatrix and really explains this detection recovery gap. Right, so this thing tells you that in the regime where we know recovery is easy, a low degree polynomial does succeed in this sense, whereas in this regime we think it's hard for recovery, this thing does not. One last setting is optimization. So for example, imagine I give you a random sparse graph, and your goal is just to find the biggest independent set that you can. So no planted solution. This also has kind of a gap. Like the actual maximum will be 2 times something, but the best known polynomial time algorithms only find something independent set half as large. And again, we have ways to basically prove that a constant degree polynomial can get all the way up to this conjectured value alg, but no low degree polynomial can go beyond that. The proof involves somehow stability of low degree polynomials along with a structural property of the syndrome phase. Okay, so just to summarize, hopefully I've convinced you that low degree polynomials successfully explain these statistical computational gaps in a bunch of different settings like detection, recovery, optimization. And the fourth one I didn't talk about is simplification or refutation. We used a few different techniques for all of these situations. And there's a couple of remaining challenges, like these are some problems we don't know how to handle, and more generally connecting the various heuristics we have hardness. Yeah, thanks. That's all.
Thanks, Alex.
Yeah, actually, Alex, I wrote my scene. I sent you my thoughts last week.
Yeah.
Sorry.
Yeah. Quick, find it.